There are a variety of different types of balanced binary search trees. We will consider two of them, AVL trees and red-black trees. We begin with AVL trees. They are named after two Russian computer scientists, Adelsonvelsky and Landis, who published their work that described those trees in 1962. AVL trees were the first type of self-balancing tree created. An AVL tree is a balanced binary search tree, which means that all nodes have a balance factor of -1, 0, or 1. Keeping the tree balanced guarantees that all the operations execute in logarithmic time, because the length of the branches are logarithmically related to the number of nodes. It is also important to ensure that the rebalancing operations are done in logarithmic time or less as well. Next, let's consider the process of recomputing balance factors and the rebalancing that may then be needed. Inserting a new leaf node can cause the height of the tree to change. A change to the tree height can cause a change to the balance factors of an ancestor's node, which is a node along the branch from the leaf node back to the root. It is possible that a change of one of those balance factors will cause the tree to no longer be height balanced. When the addition of a leaf node causes a tree to go out of balance, the out of balance subtree must be rebalanced. There are 4 cases that must be considered. The cases are characterized by the shape of the subtree that requires rotation. They are defined as the 4 combinations of left and right. You will find that there's not universal agreement on whether left and right refer to the shape of the subtree that needs rotation or the direction of the rotation. We are adopting the former convention, so we begin with an LL rotation. It means that a new node we have labeled grand is inserted as the left child of the left subtree. The addition of this node caused the balance factor of parent to increase to 2, causing the tree to go out of balance. After the rotation, the tree has been restored to being balanced. The LR rotation is illustrated in the tree on the left. Child is the left child of parent, and grand, the node that was added that caused the tree to go out of balance, is the right child of child. The tree on the right illustrates the rebalanced tree. RR and RL are the other 2 cases. RR rotations are similar to LL rotations, and RL rotations are similar to LR rotations. Keep in mind that removing a node from a binary search tree can also cause the tree to go out of balance, and the same type of rotations would be needed in that case as well. Next, we consider another type of balanced binary search tree, a red-black tree. It has several defining characteristics. First, the root node and all the null leaf nodes are black. Next, both children of every red node are black. Black nodes, by contrast, can have either red or black children. Finally, every branch has the same number of black nodes. In the tree shown below, notice that every branch has exactly 3 black nodes if we count the nulls as nodes. There are some important consequences of the preceding definition, one of which is an important invariant property. Unlike AVL trees, red-black trees are not necessarily perfectly balanced. They may not be height-balanced 1. There may be nodes whose balance factors are outside the range from -1 to +1. The important invariant is that the longest branch is at most twice as long as the shortest. This property is what ensures that the tree remains within some degree of balance, balanced enough to guarantee that the height is still logarithmically related to the number of nodes. Shown below is a worst-case example. The left subtree has a height of 2 and the right subtree a height of 4 if we count branches and include the leaf node branches. They have the same height if we measure height in nodes and exclude the null nodes. Now let's compare red-black trees with AVL trees. The get operation of AVL trees is faster because the trees are more balanced, meaning the longest branches are shorter. By contrast, the put and remove operations of red-black trees are faster because there are fewer rotations needed. Because balance factors do not need to remain in the range from -1 to +1, rebalancing occurs less often. Red-black nodes require less memory. In an AVL tree, the balance factor is a component of each node. Because of these trade-offs, most programming languages, including Java, use red-black trees, whereas databases typically use AVL trees.